Hello and welcome to this 5-minute short on relief device sizing. So this is part of a little series we've been doing around relief device sizing. And you can see on the spreadsheet at the bottom, we've got various tabs. So you can go back to the other ones to see how we got to where we've got to at this point. But at this point in our journey, we want to size a relief valve. It's going to be a vapor case. We're looking at a pool fire case. So where we're going to do this, we're going to go to size estimation. And we're going to pick one of these. So we've got various API 520 part 1 calculations. These are the most common calculations people use. If people follow API 520 part 1 most commonly for sizing. If you are using the British European standards, the 4126 series, don't worry, it gives you exactly the same answers. At this point, the standards are the same. So we haven't put in the British standard equations because they are basically the API standards, just to keep things a little bit simple. There are different calculations here. We've got an API 520 vapor because we've got a vapor case that we're doing. I've got a little video on the direct integral method. So if you get into sort of like supercritical relief, you've got non-ideal fluids, and that's the one to use. We've got the 2 liquid ones with and without certification. And I'll do a little video of that just to explain the difference between the two later on. We've got the API 520 steam equation. That is a little bit different to the British standards. The one that is different. There's no concerns about using one or the other. It's a case of pick a standard. But we've gone with the API 520 steam equation. And then we've got some 2-phase flow type sizing ones down here as well. We're going to stick with API 520 vapor, which is this one here. So this is when life gets a little bit easier now because we've done quite a lot of the hard work up front. So just to recap, we've done a wetted surface area. We've got a 16.3 square meters. We've decided we're going to look at toluene. We've got the information here and we've converted it. We've got our F factors in and we've got a required relief rate down here of 1500 kilograms an hour. So all we need to do now is then size our device. So again, we're going to fill in the yellow boxes. And again, I showed you on the last video how to look at how to generate this fizz pops. It's this box here, fizz pops. But it's really useful just to keep referring things back to this sheet. So if we do change things, then we know what's happening. So we've got our toluene, we've got our molecular weight in there. We've got our ratio specific heats. Now, because we're doing pressure relief, we should be doing the ideal gas ratio specific heat, which is that value there. We've got a Z factor, our compressibility, so we've got the vapor, it's there. We've got 6 bar gauge, 10%, let's just type those in. We're going down to atmosphere, because that's in bar A there, so we're a little bit careful of that one. We've got our required flow rate, so we're going to go back to here, and we're going to say this many kilograms an hour, and then we're going to go forward again to pick up our temperature. So really quite simple at this point to get our information. So a couple of things to note before we move on. So this Z value, so you got a little note here. So the assumption behind the API 520 equations is you've got an ideal gas. And if your compressibility is lower than 0.8 or greater than 1.1, then API says you're moving too far away from that assumption and significant errors may appear. I think it phrases it as. So we've got a little warning in here just to help people. So say I put 0.7 in, just for example, you can see that warning low Z value. What you would do in that case is then you can go to the size estimate and use this direct integral method. So that's kind of one of the reasons why you would use that method. So little warnings in there. We try and put these things in to try and help people. Ultimately, it's up to the engineer to put the information in, decide what it means and what the answer is. But we're trying to do as much as we can do to help people, guide them along. So the green box is there doing the calculations. So we've looked at our relieving pressure. We've got our choking pressure. It's checked whether it's choke flow or not. And this sheet will detect whether you got choked flow or not in the valve and use the right equation. So if it's subcritical flow, you haven't got a choke, then it will use a different API equation in the background. We then got our coefficients. So our discharge coefficient. So we leave that as 0.975 in there. we're going to say it's not a bounce balance valve, but I'm going to put a bursting disc and I'm going to put a 0.9 in there. So that's going to give me my KDA required. And then I'm going to choose a valve. So if I look here, I need 195. So technically, these are the API 526. I could go for 198, and that is suitably sized. From a mathematical point of view, if you were that close, you would probably go up a size. I mean, there's no hard or fast rules about when do I go up a size, when do I not go up a size. I think a lot of people will go less than 3 square millimeters as a safety device will go up a size, so we'll go for a G, which would be 325. But again, that's a very much a engineering judgment type conversation. There's no rule I can give you that says if you win plus or minus X%, this is what you should do. Technically, an F would be fine, but a G practically feels better. Now, there's a couple of things going on in here. We're giving you your rated valve capacity. So this is what the vendor would guarantee, given the fact you've got a 0.975, you've got a bursting disc, you've got 325 square millimeters. That is the rated capacity of your valve. That is what it will pass. Or, yeah, that's the theoretical maximum it would pass. That's what the vendor will guarantee. So we need to make sure our required relief rate is below that. But for those of you who are into your D ratings and understand relief valves have 2 flow rates, what the valve will actually pass if it fires in anger, in this case, is this value here, this 3168. So what that has done is taken out the bursting discs. So it's got to assume the KC is 1, and it's taken out this 0.9 safety factor. So under the standards, be it API standards, be it British standards, you need to derate the valve. You need to add a 0.9 into the equation. So what is a safety factor? So what we guarantee the valve will pass is 11% less than what it will actually pass. So that's what that value is there. So to get that value, we've assumed KC is 1. We've assumed that 0.9, well, I assumed it's a European API valve, so it will be 0.9 in that sort of situation. So we've taken that out. Now, sometimes you can get actual published KCs. So this KC here is 0.9 is what API recommends if you don't have a published KC for your bursting disc. And what we've done down here is we've said, well, that's quite a conservative number. So for our actual capacity, we're going to assume it's 1. You can get published KCs now. So you might have, say, a valve that's got 0.95 as a published KC. You could use this down here because you know that's a fact and adjust that actual capacity based on that. So that's how you'd handle that situation. But in this case, we'll assume we're very much at the start of things. So we're just kind of using generic numbers. But that's given me my rated capacity, my actual capacity of the valve. I've sized my valve up here, 325. And of course, you don't have to use API 526 numbers if you're using something that's not sized to that. You would just type that number in here. This table is purely here to help and aid. It doesn't have to be that. As long as you've got a KD from a vendor, an area from a vendor, you can use those values and size your valve. Thank you very much.